Hello, everyone. I'm Zheng. I'm a postdoc at Université de Lorraine in France, working on dependable hybrid systems. Today, I want to share a refinement methodology we find useful for hybrid system design with safety constraints. People probably refer hybrid system in different contexts. But in our context, is that a hybrid system exhibits both continuous and discrete behavior. It can flow differential equation to flow continuously, or performing discrete jump to follow different dynamics. Washing machine is a hybrid system. You put it in a mode, washing for an hour, then the machine follows its dynamics, swirl your clothes and clean them. Then it eventually jumps to stop mode. It's an open loop system. You give it instruction, it finishes what is being asked for. At the end, no matter clothes is clean or not, it terminates. It's still a closed loop system, which will be our focus. Closed loop system based on system state to iteratively progress towards a desired outcome. For example, a patient with diabetes can benefit from a hybrid closed-loop insulin delivery device. At each cycle, it detects the patient's blood level, sent to the controller. Controller uses such information to predict how much insulin should be injected and ask insulin pump to inject that amount to keep patient's blood glucose level at a safe range. Then move on to the next cycle. Closed loop hybrid system is in our daily lives everywhere. It's in our car, it's on our body, it's around our environment. And they need to design there for safely. Otherwise, it not only costs money, but also lives. For example, we don't want our cruise control keep hitting each other all the time. Neither we want a smart house that make our life miserable by keep cooling down while it's -degree out there. Design safe hybrid system is our noble goal, but it's challenging due to theoretical results on modeling the physical world and our understanding of the environment, among many other things. However, this field of research is moving fast. And in this session, I want to give you a flavor of event B, how we are dealing with this kind of problems. The example I borrowed to illustrate our approach is the simple smart heating system. It operates in two modes, on and off. Each mode follows its own simple dynamics. The room temperature is sampled every delta seconds by a sensor and sent to the controller. The controller takes the sensor information, the current mode, need to decide whether mode needs to be switched to maintain the room temperature at the safety range. Moreover, if it decides to switch mode, there is going to be Tx second of inertia. That is, the system will follow the dynamics of current mode for Tx seconds before follow the dynamic of the switched mode. The problem is therefore in this case study, design the control logic that decides whether mode need to be switched to maintain room temperature at a safe range. We have two goals while developing such system. First is to use event B as a logical framework to not only develop such system, but also reasoning its safety in a machine checkable way. The problem we have is that we have seen many nice, beautiful proof that reason hybrid system safety, but we take a lot of time to manually understand is it proved. And in order to do that, we have to manually understand what is proved, how it is proved, under which condition it is proved, etc., etc. Inventing a proof is fun, but checking it is a highly repetitive work that computer is really good at. So it would be really nice if we could have a computer help us to check the proof. I mean, you send a proof in, the machine does the check step by step, replace your proof and tell us whether eventually the proof is correct or not. Of course, the proof checker can be wrong, but in my opinion, it's a motivation for proof checker engineers to work harder. Our second goal is to reduce the effort that make a design implementable. The problem is that we find we as engineers usually follow our hearts that thinking something intuitive, but then take a lot of time to make it work with the hardware. How about taking the implementation constraints in your problem abstraction at the first place, so that we can reduce the effort to make the design implementable later on? To achieve these goals, we develop a refinement strategy. The input is a specification with safety properties of the hybrid system to be developed. The output is some code we can put on a microcontroller or a hybrid automata that allows to simulate the behavior of our system. From the inputs to the outputs is a list of refinement steps. Each step tries to make a specific part of our hybrid system design more concrete, while inductively verifying that a safety property promised a consistently hold at each refinement step. To illustrate this strategy in more detail, let us consider back the heating system example. We're first going to make our problem specific to the problem we are going to study, where we first specify there is going to be a system trajectory T that represents the room temperature over the entire time span, and it's between the safety range magically. In the next refinement, our refinements aims to make the construction of temperature trajectory T more precise, by specifying it needs to be inductively constructed by a piecewise time series. To achieve this, we introduce cycles, where we assume that there is a variable now to track cycles, and each cycle is an interval between now and now plus the time difference delta. Assuming that we already have a time series up until now that is safe, then by appending another piece of safe trajectory for an additional cycle, then it is intuitive that the cycle up until now plus delta is safe. The cycle recurs towards time infinity to inductively construct the time series for the room temperature T that is promised in the previous refinement. This kind of induction is used everywhere in our refinement, and is the key that helps us to build a machine checkable proof. Then we refine the inductive construction step, specifying that each piece in the time series to be constructed experience the full cycle of a simplified closed loop architecture. Please see at the bottom of this figure. At each cycle, the discrete control to be designed as a black box first need to predict a safe trajectory over the next cycle. Then the discrete control pass the initiative to the continuous system, where the predicted trajectory is used for system progression. Finally, the continuous system passes the initiative back to the discrete control for the next cycle and close this loop. The intuition of this refinement is that by the closed loop architecture, we delegate the construction of a safe trajectory at each cycle to the discrete control. In the next refinement, we aim to concretize the discrete control by specifying when certain events are detected, what action should take. The key problem is what kind of events to detect. Taking our heating system, for example, an intuitive design is that if we are in the on mode that increase the temperature, and the current temperature is less equals to Tmax, then we decide to continue increase the temperature for the next cycle. This design attempts to detect the precise threshold to react, which would be fine if we're sensing all the time. But as our specification said, we only sense the temperature periodically. In other words, we could have the current temperature at exactly Tmax. Then following this control logic, we continue increasing temperature for the next cycle. By the next sampling time, we would outside the safety range, hence break the safety rights. Not good. So we need to cooperate with hardware constraints in our design. We're thinking it may be a good abstraction just to detect an imprecise threshold to react. For example, in the heating system, we could say if the system is on mode and the current temperature is not near the Tmax, we probably can survive for another cycle. Then let us stay the on mode for the next cycle. You may ask how to quantify the near to Tmax or to determine whether we can survive for another cycle. They're too vague. Exactly, that's the point. That's what we need to concretize in the next refinement by a worst case analysis. To do that, let us first review our specification in more detail. The fact that the system works in two modes implies that the control logic can only activate between them. The simple dynamic gives us some hints on their monotonicity. The sampling time requires us to make a decision that ensures between current and next sampling time would be safe. The fact about switching time tells us there is a cost of switching mode, which we need to take into consideration when we design the control logic. So after we read the description of our heating system, we can start to concretize our control logic. For example, for the case we just considered, we can quantify that when we are at the on mode and the following on mode for the next sampling time plus the activation time is still safe, then we can survive by staying on mode for the next cycle. Why this is safe? The fact that the temperature prediction at the now plus sampling time guarantee us we can survive for the next cycle, right? And the extra prediction that the plus T-act is safe guarantee us even if we need to switch at the next cycle, we have enough time to react to the inertia caused by the switching mode. That's why this case is safe. So we do this kind of analysis for all the cases that need to be considered, and summing them up together. It's basically represent as an automata. If we visualize such automata, it will be something like shown here. For example, the top left corner is the case we just illustrated. It says that if we are at the on mode and following the dynamic of on mode for the next sampling and the TX seconds is still safe, then we can stay on mode for the next cycle. We can then put such automata into tools like Stateflow of MathWorks for simulation, or we could encode such automata as an algorithm in C or Java and put them onto a microcontroller for test. Thanks to the developed refinement strategy, we can design a hybrid system while verifying it has the intended safety behaviors. The table demonstrates the verification efforts developed using Event-B language in Rodin IDE. As we can see, 68% of proof obligations can be automatically discharged. This is first thanks to the auto-prover of Rodin and some meta-theorems we have developed. Besides, 32% of proof obligations are discharged manually. This is because the lack of native support in Rodin, which we agree that more engineering work is required in this direction. About verification soundness, our verification is based on extremization of real numbers and some domain properties of the systems. To ensure these axioms do not cause unsoundness, we minimize a set of core axioms and build other needed axioms by lemmas. About completeness of verification, we lack support of automatic invariant generation. The implication is that it could cause incompleteness. That is, something supposed to be provable, but due to the missing invariant, we cannot prove it. So users needed to add them themselves. But we find that there are some tools like Pegasus for invariant generation of hybrid system that could be integrated in our work in the future. We think that to improve our current work, we will focus on maybe developing more case studies, that's for sure. And we also want to integrating with advanced reasoning and modeling tools on top of our strategy for interoperability and automations. For example, integrating with Pegasus for automatic invariant generations. Also, that technology transfer could be beneficial. I mean that transfer our current methodology to other programming language or frameworks for cross validations. So our model in event B is publicly available at the following GitHub address. Please feel free to contact us if you have any suggestions or questions. We would be happy to know them. Thank you very much. That would be all from me.